welcome back. So we were discussing decision trees, okay, and we stopped at a point where we saw that there is a tie between two attributes. Okay, the tie between outlook and routine, where we had no way of knowing until we come up with some heuristic which one to choose as a splitting condition, right? Okay, so this gives rise to a heuristic known as entropy, all right, which is sort of a measure of chaos in your data. Okay, so what it means is, if, and it's directly proportional to the amount of chaos. And by chaos, what I mean is, we are not able to determine, a clean split between the two different levels of the class. Okay, and so what it also means that if your one particular attribute, okay, has high entropy measure, right, that amounts to high chaos. Okay, so what's the idea? The idea is that we want to reduce chaos or entropy in the system, by choosing the correct attribute. If you have seen in the previous examples when we are working through the data, we saw that if it's overcast, there is no confusion at all. There is no mixture of the class levels. We are perfectly able to split, right? So if we are greedy, we start with overcast as one of the starting attributes, right? Okay. So what really entropy is like it measures the impurity of a sample. It measures the, and what do I mean by impurity? Like if a sample has, 2 instances of positive class and 3 instances of negative class, or vice versa, right? That's impure. What's pure? if it has just purely all examples which belong to one particular class and no examples which belong to the other class. Okay, all right. So ideally that's what we want, because that's where we would stop, because then that means that we have been able to correctly classify the class levels. Okay. All right. So typically what happens is, let's begin by assuming that S is a sample. Okay. We are going to use this throughout as S. Okay. And I is a set of outcomes. So I equal to 1 to n. If I is 1 and 2, then it's a binary classification problem. Okay. Okay. So for outcomes I equal to 1 to n, the information entropy or just entropy of the sample is nothing but summed over all classes, right? Okay. All right. And if n is equal to 2, it's a binary classification problem, right? And there you can, choose one as, this is the probability, okay? One as p and the other one as 1 minus p, okay? All right. So this is the probability of, correctly classifying the ith class, okay? All right. So the idea is use this heuristic to figure out the attribute with the lowest entropy, because that's what you are going to do. That's a job, right? Now there is a problem here. If probability of correct, classifying a sample correctly could be 0, right? So you can have p of I, this pi can be 0, right? If pi is 0, this is 0 log of 0, which is undefined, and we have a problem. In order to fix the problem, there's an easy fix. Okay, we take a limiting criteria and we set 0 log 0 as identically 0. Okay, all right. Okay, so a formal definition of entropy is, it comes from information theory and coding theory, right? Okay, so the entropy of a sample is the expected number of bits. So this is a statistical expression, right? The expectation, you know what expectation is, right? I mean, probability times, the if it's a continuous density function, it's integral of xfx. If it's not, it's just integral of the summation of xf, where the function itself is the log function. Okay, so the expected number of bits needed to encode class, a particular class, right? Assuming that this is a binary classification problem, let's say I have two classes, positive and negative, right, of randomly drawn numbers, of S. Okay, and this has to be done under the optimal shortest length code. You understand the connection to the decision tree? Because what you have to do is to find the expected number of bits to encode a class level. Okay, and when you are randomly drawing instances from the sample, right, and it's your optimal shortest length code, which actually corresponds to a shortest decision tree. Okay, all right, because you would want to keep your decision trees short in order to avoid unnecessary computational expenses. Okay, all right, and so the optimal length code actually assigns a negative log to the base 2p bits, okay, to messages having probability p. So if I have to write it down for a binary classification problem, is something like this. If you, let's say, the probability of correctly identifying the positive samples, the probability of correctly identifying the negative samples. Okay, so this is the expression for entropy E of S for a two class problem. Okay, all right, let's take a deeper look at what entropy is, okay, before we move on, because it's sort of easy to visualize entropy because the base is log 2, and if I just take the probability of identifying the positive classes, and this is along the vertical axis I'm plotting entropy. So the numbers are minus p log of p to the base 2, right? Okay, so as I said, I make the assumption that when when p plus is 0, the entropy is 0, just to avoid the undefined outcome of that function. Okay, and it's also easy to see when p plus is 1, which means the probability of identifying all positive samples is 1. You have identified all positive samples correctly. Log of p plus being its log of 1, it gives us 0, right? So when p plus is 0, the entropy is 0, and when p plus is 1, the entropy is also 0. Okay, all right, and so what will happen in between? So there is this value at 0.5. Okay, this is graphically speaking, right? 0.5, and then we will see that the graph peaks at 0.5, comes down. Okay, it's sort of smooth, right? And this is where you have the maximum entropy. Okay, and it reaches maximum entropy when p plus is 0.5. What do we make of this? Well, it's a it's sort of this, right? When p plus is 0.5, that means the probability of correctly identifying positive samples is 1/2. That also means the probability of correctly identifying negative samples is also 1/2. It's like a coin toss, correct? I mean, you're tossing a coin and you don't know, it's like outcomes are not predetermined, assuming that it's a fair coin, right? And so this thing is not useful, right? I mean, the maximum entropy value is not useful, because when it reaches maximum entropy, you are in trouble. I mean, you should have either one of the two. I mean, you should have the p plus, the probability of correctly classifying positive samples should be towards 1, so that the you are able to classify the positive samples correctly. And obviously, if you do that correctly, you should be able to correct the classify the negative samples correctly as well, right? Okay, so maximum entropy is achieved when all outcomes are equally likely, right? Okay, and minimum entropy is achieved when one outcome is almost certain and the other outcome are not. Okay, all right. So let's look at the functional property of entropy, and we just recall that log of p to the base 2 is nothing but log of p divided by log of 2. Okay, simple enough. And we have this expression of entropy that we write from the previous, if you recall. And I'm simply going to write this because since it's a 2-class problem, right? So I'll just assume that p plus to be p, and therefore p minus to be 1 minus p. Okay, all right. Now, since we are trying to find an optima of this, right, a maxima rather, I mean, we go back to calculus. It's a standard technique. So, and we are doing that with respect to p, right? Okay, and so it's should be a straightforward exercise where you have log of p plus p times 1 over p plus 1 minus p 1 over 1 minus p with a minus sign, and then log of 1 minus p times the minus sign. Okay, all right. And if I simplify this further, I'll get this. Now, what I want the critical points, right? So, the condition for critical point, when this guy has to be 1, that's the only option, right? So, when this guy is 1, p is exactly equal to 1 minus p, right? And that means p is nothing but 1/2. This is exactly what we observed here. Okay, recall, this is exactly what we have observed. And when p is equal to 1/2, 1 minus p is also equal to 1/2. But this is a critical point. Okay, so this is a critical point. We don't know whether this is a point of maxima or minima. So what we do is we take the double derivative, right? Okay, just test for the double derivative. Okay, and so this is nothing but minus 1 over log of 2. And if I do it carefully, it's minus 1 over log of 2 d of dp log of p minus log of 1 minus p, right? And this is minus 1 over log of 2 1 over p minus 1 over 1 minus p, but then there is another minus, and minus makes it a plus. Okay, right. Now, I mean, it's easy to see for the value of p, which is 1/2, right? So this guy is positive, this guy is also positive, so this thing is positive, right? 1 over log of 2 is also positive, right? But you have a minus sign. So that means you have a negative. So for this critical value, p is equal to 1/2, your second derivative is negative. That implies that p is equal to 1/2 is a critical point and is also a maxima. So establishing the fact that we observed, what we observed visually is that at p is equal to 1/5 or 1/2 or 0.5, we achieve maximum entropy, right? Okay. So the question is this useful, right? I mean, imagine an attribute where half of the time, you are sort of, the outcome is true and half of the time the outcome is false. It's actually not useful for you, right? Okay. So you cannot use this information for prediction of the class levels, right? Because you are never sure. Your accuracy would be around what? 50%, right? Okay. So therefore, we have to improve upon this. So there needs to be some improvement. Okay. Some improvement is necessary. So basically another heuristic, which is called as information gain. Okay. So let's talk about this. So the question is, my goal has been consistent. What I want to do is I want to reduce the entropy of the system. Okay. All right. So therefore I define something from the sample. I begin from the sample. So I choose a sample and I choose an attribute, right? Okay. So, and I determine how much, because I chose this particular attribute, how much reduction in entropy is caused by that particular attribute. Okay. All right. So formally speaking, this is expected reduction in entropy, expected sorting of the attribute A. Okay. All right. In other words, I begin with the entropy of the complete sample, right? Okay. And it turns out that it's useless, right? So I need to reduce this. So therefore I introduce a minus sign. And then for over all attribute values, okay. So S I know is a set of examples, A is an attribute, and this SV is nothing but a subset of S for which the attribute A has value V. So the values are all possible values that attribute A can take. Okay. These are all values of the attribute. Okay. So let's take an example. Let's choose the attribute routine from the earlier example. Okay. So there are two possible cases, indoor and outdoor, right? And these are the values of A, assuming that we choose A as the routine attribute. Okay. All right. So for each of the attribute, A, the gain is A. The gain is A. What it will do is it will count how many examples. So gain A will count number of examples in the set. Okay. So for example, let's say values of outlook. What are the values of outlook? If you recall, these are sunny and cloudy, right? And the sample S has 3 examples and 4 examples from sunny and cloudy respectively, right? Okay, and what are SV now? SV are, so what you are trying to do is you are trying to count the examples belonging to each of the attribute values from the sample, right? And if you recall, this is what we had. Based on that example, whether I should wear coat or not, right? Okay. So, how do I compute gain is A? Gain is A in this case is that gain S, and you have chosen outlook to be your attribute. So what will happen is the entropy of all the examples minus. Now what are the V values? Look, the V values are the values for sunny and cloudy. Okay, sunny and cloudy. And so it will be easy to compute the cardinality of SV, and we already know the cardinality of S, which is 7 samples, right? And then the entropy of multiplied by the entropy of S of V. Okay, I can give you a useful tip. I mean, you need to calculate entropy in general, but if you have things like this, I mean, there is a useful tip here. I mean, if I know that there are 10 positively classified samples and 0 negatively classified samples, the entropy of the sample is 0. And if it is 0 plus 10 minus, the other way around, in that case also the entropy of the sample is 0. And if it's 5 plus and 5 minus, actually the nightmarish case, the entropy of the sample will be 1. Okay, so with this in mind, let's just take a look at the example, because that example has 14 instances. So I'm not going to waste time in writing down all those 14 examples. So let's just go to that particular example now. Yeah, this particular example. Okay, I hope it's visible. And so I mean, we have a total of 14 training examples here. Right. Okay. Now, out of these 14, I mean, you can see that I have 1, 2, 3, 4, 5 examples of sunny. Okay, and bunch of examples of overcast. Right. Okay, and it's a play tennis example. So the attributes are outlook, temperature, humidity, and wind. Right. And what I can observe here is that when it is overcast. Let's look at this: overcast, 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 overcast. In all of those 4 cases of overcast, the outcome is play. That's perfect. So it's like a 4 plus 0 minus, right? Okay, so I really don't need to worry about that overcast attribute at all. Okay, so let's look at some of the other things. So let's look at humidity. Okay, all right. So humidity has like how many high examples? 1, 2, 3, 4, 5, 6, and 7. So, and out of this, when you have, your outcome is, whether you play tennis or not, right? So it's when it's high and you are not playing tennis. How many examples do you have? Right? I think you have 4 examples. And when the humidity is high and you want to play tennis and you play tennis, that you have 3 examples, right? Okay. So this is P plus, this is P minus. So what you do is you take the sum of the P plus is 3 over 7 times log of P plus and plus 4 over 7 times log of 4 over 7. Take the sum of it, and that's your entropy, right? Okay. And that entropy is 0.985. Okay. When humidity is normal, actually, most of the cases you will see, in fact 6 out of the 7 cases, you will see that you play tennis. Okay, so this is actually a good example, right? Because you have an overwhelming less chaos in the system. I mean, you have an overwhelming verdict in favor of playing tennis when the humidity is normal, right? So you can see the entropy is sort of low, at least significantly lower than what you observed in the previous case, right? Now, using this, I mean, can we compute the gain of the sample based on the first attribute humidity that we chose? Okay, so the entropy of the humidity, which is like 9 plus and 5 minus of the total number of 14 samples, right? So it's like 9 over 14 log of 9 over 14 plus 5 over 14 log of 5 over 14. If you do the calculation, you will see that is 0.940, right? So if you recall the formula is that you start with computing the entropy of the sample based on that particular attribute, right? And that is 0.940 minus the attribute values of humidity. The attribute values of humidity are 2. We have high and normal. So when it is high, it's like minus 7 over 14 times the entropy because of that, and then when it's normal, it's, as I said, it's 7/14 again times 0.592. So in the end, your information gain is about 0.151. Okay, all right. So we will continue this example in a bit.